If you have an n by n matrix, to find out if it has an inverse, you can just check and see if the determinant is not zero. And I think we talked about this already. I just want to go all the way through this problem. So to find out if this 4 by 4 matrix is invertible, we're going to just find the determinant. And so to do that, we're going to use the first row because it has a 0 and it has small numbers. So we're going to use that row. So the first thing we're going to do, of course, is just start with the first element of that row, which is -2. We're going to cross out the row and column, and we have that smaller matrix left. I'm just going to write out what we have. So -2 times the determinant of the smaller matrix times -1 raised to the row plus column. And then we're going to move on to 0, which is just going to end up being 0. So we won't even worry about that smaller matrix. And then we'll move on to 1. So we'll have 1 times the leftover matrix, the minor, and we'll multiply that by -1 raised to the row plus column. And then we'll go to 2, which is the last row, first row, last column. And so we'll have 2 times that matrix that's left, the minor, and we'll multiply that by -1 raised to the row plus column. All right, so this is what we have. And we're going to have to go ahead and find the determinants of all those 3 by 3 matrices. And so we'll just go ahead and go to the next slide to do that first matrix: 2, -2, 5, 3, -1, 1, and 4, 2, 1. So we're going to do the first column of this matrix. And so we'll have 2 for our first element. So 2 times -1, 1, 2, 1, multiplied by -1 to the row plus column. And then we'll go on to 3. So we'll have 3 times the minor and -1 to the row plus column. And then we'll have 4, and we'll do 4 times the minor, and we'll have -1 to the row plus column. And now we can just work that all out. We'll have 2 times -1 minus 2 times 1 squared, -1 squared, which is just 1. And then 3 times -2 minus 10. -1 to the row plus column is -1. And then 4 times -2 minus -5. And -1 to the fourth is just 1. And then if we multiply all that out, we're going to get 42 for that determinant of that first 3 by 3 that we have. So now we're going to do the next 3 by 3 in the original determinant of the 4 by 4 matrix we're trying to do. So this one, we're going to use 6 times the minor times -1 to the row plus column. And then we're going to go on to 5. We're using the first column. So 5 times the minor, 2, 5, 4, 1, times -1 to the row plus column, 2 plus 1. And then for the last thing, we have 0. So that's good. All right, now we're just going to do 6 times the determinant. So 3 minus 4, and then -1 squared is 1. And then 5 times 2 minus 20. And -1 cubed is -1. And so we multiply all that out, and we get 84 for that second determinant. And the third determinant we have, so we'll use the first column, and we'll do 6 times the minor, and times -1 to the 1 plus 1, and then we will do the 5. 5 times 2, -2, 4, 2, and -1 to the row plus column, and that's all we have because there's a 0 last. And we will just multiply all that out. So 6 times 6 minus 4 minus -4, and times 1, and then 5 times 4 minus -8, and that will be -1. And multiply it all out, and we're going to get 0 for that last determinant. All right, so here's all the stuff, and we have done all those 3 by 3s, and now we just have -2 times 42 times 1, and then 1 times 84 times 1, and then 2 times 0, which will just be 0. So we're going to have -84 plus 84 plus 0, which turns out to be 0. And so that means the matrix is not invertible because it is equal to 0. So the only matrices that are invertible, their determinant will be non-zero. So this one is not invertible. All right. So Cramer's rule says that if you find the determinant of the coefficient matrix, and then you find the determinant of the coefficient matrix with the column replaced, one of the columns replaced with the constants, whichever column you replace, so if you replace the x column, you can solve for x by dividing the determinant of the coefficient matrix with the constants replaced in the x column divided by the determinant of the coefficient matrix. And that's a lot easier to write down than it is to say. So we're going to solve this system of equations using Cramer's rule. So the way we're going to do that is we're going to look at the coefficient matrix first. And the reason we're going to do that is because if the coefficient matrix turns out to be 0, we're not going to be able to use Cramer's rule because the coefficient matrix, the determinant of the coefficient matrix, is the denominator when we are working out Cramer's rule. So if it turns out to be 0, we don't even need to try to do this. So the coefficient matrix, we've got negative 11, 6, 2, negative 5. And so that is 55 minus 12. And so that is 43. So that's not 0, so that's good. Okay, so to find x, I'm going to have this fraction. It's going to have the determinant of the coefficient matrix on top, except I'm going to replace the x column with the constants. So the x column is going to be 4, negative 3, the constants, and the y column will just be exactly what it is, which is 6, negative 5. And then the denominator is going to be the determinant of the coefficient matrix, which we found over here, which is 43. So that means that x is negative 20 minus negative 18 all over 43, and that is equal to negative 2 over 43. And so that is x. To find y, we're going to do the same thing, except we're going to replace the y column this time with the constants 4, negative 3, and the x column will be the coefficients of x, so negative 11 and 2. And then on the bottom, we're going to have 43 again. The coefficient matrix, the determinant of the coefficient matrix, always goes on the bottom. So this is going to be 33 minus 8 over 43. And so that is going to be 25 over 43. So this is the solution to that system of equations, negative 243 and 25 over 43. So I'm going to go ahead and run through this 3x3 system just to show you that how we work with Cramer's rule. It's the same way I just did it. I'm going to go really fast because you can pause it if you need to. So we have these three equations, and the first thing we're going to do is find the determinant of the coefficient matrix. And we do that. We're just going to use 2, and so we're going to have 2 times the minor, 7, negative 2, 3, and we're going to multiply that by negative 1 to the row plus column. And then we're going to move on to negative 5. We're using the first column here. So negative 5 times the minor, and multiply that by negative 1 to the row plus column. And now we're going to move on to 9. And so we'll have 9 times the minor and multiplied by negative 1 to the row plus column. And we're going to multiply all that out. And it's just going to look like this. And when we do that, we are going to get negative 222 for the determinant of the coefficient matrix. And that's not 0, so we know we can use Cramer's rule for this. If it had turned out to be 0, we wouldn't be able to use Cramer's rule because that is going to go in the denominator of all of our fractions we're going to use to solve for x and y. So here we are. We've got the determinant is negative 222, and we're going to go ahead and solve for x. So the determinant of the coefficient matrix with x replaced, the x column replaced with the constants 11, negative 6, 4. And so that is what we're doing. We're replacing the x column with the constants in order to solve this system of equations for x. And so that is going to be 11 times the minor times negative 1 to the 1 plus 1, and then negative 6 times the minor, times negative 1 to the row plus column, and then 4 times the minor for the 4. So when we multiply all that out, we're going to get 77. And so that means that x is going to be that value over the determinant of the coefficient matrix. So 77 over negative 222, that is our x. That is the value of x, the solution for x for this system of equations. Okay? And you would do the same thing for y and z. So you would just set it up the same way. To solve for y, you would have the coefficient matrix replacing the y column with the constants. So 11, negative 6, 4 would be in the y column. And the x and z columns would just be whatever their coefficients are. We don't change those at all. So 5, negative 2, 3. And then the denominator is the determinant of the coefficient matrix, which we already found out is negative 222. And so you would work that out, and that would be your y. And then for your z, you would do the same thing. The denominator is still going to be negative 222. And the numerator now is going to be the 3 by 3 with the z column replaced with the constants. So the z column is going to have 11, negative 6, 4. And the other two columns will just be the coefficients of those columns. So negative 3, 7, negative 2. So that's going to be your z. Those would be x. You already got x, and now that is going to be y and z. And when you write your answer, you will write it like this as a coordinate triple. All right, last of all, we'll try to use Cramer's rule to solve this system. And we're going to find out that this system can't be solved with Cramer's rule. So we would set it up. We would first of all find the determinant of the coefficient matrix. So the coefficient matrix is 1, 3, negative 2, negative 6. And when we multiply that out, we're going to have negative 6 minus negative 6. And so that's going to be 0. So we can't use Cramer's rule to solve this system of equations. And if we were to solve it using Gaussian elimination, we'd have 1, 3, 6, negative 2, negative 6, negative 12. And so you can already see that these two equations are the same line. And so that means that there are an infinite number of solutions. And to show that, you can just solve for x here. So you'd have x equals negative 3y plus 6. And so when you write your answer, you can write y as just y, and then you can write x in terms of y, negative 3y plus 6. You could have write this also with x in the x position, and then write y in terms of x, but it's just, it's more of a pain to solve for x in these equations, to solve for y in these equations than it is to solve for x. So it's easier to write x in terms of y for your answer.